So in this lecture, we're going to start a chapter on integration. So what we're going to do now is going to look a lot like Riemann sums. So first we're going to say we have this interval AB. We have a partition. A partition of AB is a set of points. We're always going to write the points in increasing order, although sets don't implicitly come with an order. We're going to assume these points are written in increasing order, such that the first point is A1 and the last point is AB, and in between they're increasing. Okay. So if I have two partitions, P and Q, partitions of the same set AB, we say Q is a refinement of P if Q contains all of the points of P and possibly some others. Right? So if P is a partition of AB, then the mesh of the partition is just which we denote with the P with double bars around it, it's just the maximum width of one of the intervals in the partition. So we have A, B, partition is going to be, chop this up into pieces, and then I'll look at the lengths here, and the biggest length like this is the mesh. Okay. So if I have a partition P of this interval AB, and if I have a bounded function defined on AB, then we define this capital MI and the lowercase mi. The capital MI is the supremum of function values on this ith interval in the partition. And look at x's between xi minus 1 and xi, and look at the function values there. I take the supremum. Okay, so for example, so here this would be x0, x1 in this partition. I would look at the function values, take the supremum of those. So here, because we've said it's a bounded function, the supremum is finite. Okay, so I'd look on this interval, take the supremum of the function values here, and that would be m1. Then I would move to this interval, take the supremum of the function values here, and that would be m2, capital M1 and capital M2. And I would do the same for the infimum. Okay, look on the first interval, find the infimum of the function values here, and that would be lowercase m1. Look at the second interval, take the infimum of the function values here, that would be m2. Okay. So the upper Riemann sum of f on this interval with respect to p is the sum. So it's the xi minus 1, which sometimes we call delta xi. It's just the length of interval number I. Okay. And I multiply that by the supremum. Right, the supremum of the function values on the interval number I. So for example, I have a function like this. That's a, that's x0, and then x1, then x2, x3. So I'm going to look at the interval from x0 to x1, find the supremum, which looks like it's here. I take that function value, that function value is m1. And then look between x1 and x2, find the supremum, it looks like it's here. And then x2, x3, find the supremum, it's right there. Okay. And then that's giving me my rectangles for Riemann sum. So m1, m2, m3 would be those heights, and then the xi minus 1 would be the widths. And multiply those, add together. The lower sum is similar, except I'm doing it with the infimum of the values. So I take the smallest values on each interval. So I just said the infimum will be the smallest values. That's not technically true if my function is not continuous. Then the supremum and infimum here are not necessarily attained. If my function is continuous, then the supremum is actually a maximum. Okay, so this mi will be attained, and this lowercase mi will be attained if my function is continuous. And all the cases of interest will be when the function is continuous, but we're going to make these definitions for any bounded function. These definitions make perfectly good sense for any bounded function. Okay. So more generally, if I have this capital F, which is a non-decreasing and right continuous function, then I can define this upper with an F sum. It's similar, except instead of having an xi minus 1 here, I have f of xi minus f of xi minus 1. So here, if I look back over here, this xi minus 1 I want to think about this as being like a weighted average. So these mi's are the values that I'm averaging, and this is telling me how much weight to apply. Okay? So if I have a wider integral or a wider interval, then that interval gets more weight. Okay? So this is exactly the same thing, except I might be in a situation where I don't want the interval weight to just be its length. I want it to be something else. Okay? So this will occur a lot in this kind of thing occurs a lot in statistics, although they don't necessarily show it by this name. But when you deal with CDFs, you're dealing with things like this all the time, even if they don't say it this way. Okay? So you have an upper F sum and a lower F sum. So we call these Riemann-Stieltjes sums. Okay? Okay, so Stieltjes. Okay? So we're going to have a Riemann integral and then a Riemann-Stieltjes integral. And there are even Lebesgue integrals and Lebesgue-Stieltjes integrals. If you want to see those, you can go to measure theory. That's beyond the scope of this course. So I'm going to say something and not prove it. I'm going to leave it to you to prove as an exercise. I think it's a pretty easy exercise. If Q is a refinement of P, so here, assuming F is a bounded function on AB, Q and P are partitions of AB, and Q is a refinement of P, then I have this string of inequalities. So first of all, I want to focus on this one. The lower sum of F with respect to Q is less than or equal to the upper sum of F with respect to that same Q. That's obvious. So let's go back. The upper sum and the lower sum for the same partition are given like this, and these capital MI's are greater than or equal to these lowercase mi's, so this entire thing is bigger than or equal to this. That's obvious. Okay? So this one is obvious. Right? This inequality is obvious. This one is not so obvious, but once we prove this, then we'll also have this one basically for exactly the same reason, but upside down. Right? So let's see, what are we saying here is if I take P and then refine it by taking the partition and adding new points, then the value of the upper sum can't increase. It can only decrease or stay the same. And the lower sums go the opposite way. If I take this partition P and add new points to it, then the value of the lower sum might increase or might stay the same, but it cannot go down. Okay? And so if we want to prove this, so all of our partitions are finite partitions, so basically what I'm saying is if I take P and add new points to it, the value of the upper sum cannot increase. Well, if I want to prove that, I can prove it by induction. And in order to prove it, I would really just need to know that if I take P and add one new point, then the value of the upper sum doesn't increase. And if I take 10 new points, I could think about that as taking P, adding one new point, and getting a new partition, and the upper sum doesn't increase, and then adding the second point, and it still doesn't increase, and I keep adding points one at a time. And I know that every time I added 1 point, the upper sum did not increase. And so we want to understand, so if I get Q by taking P and adding 10 points, I can think about adding those 10 points one at a time and knowing that each time I add 1 point, the upper sum doesn't increase. So now we just have to know why the upper sum doesn't increase when we add one new point. Right. So when I think about the entire, so I have the function, right, I have x0, x1, and then xn, and let's say I have xi minus 1 and then xi, and this is my partition P, and I get some upper sum from this. Right. So let's say I add a new point, and my new point is in between xi minus 1 and xi. It has to be between two of the points, right? So it's going to be in between two of the existing points. It doesn't really matter which two. And so if I think about, okay, now I'm going to take the upper sum for the new partition. Okay? So x0 to x1 is unaffected by the new point. Right? x1 to x2 is unaffected by the new point. The only one of these rectangles, which is going to change between P and Q, so P was before I added the new point and Q is after, the only thing that's going to change here is this this one interval in P is now going to be two different intervals in Q. And so we can just kind of need to focus on that, and that's what's here. So here's how it would look in P, is I take the supremum over the whole interval, and then I get my rectangle by multiplying this width by this height. And now in Q, if I add this new point x star, then in Q I'm going to take the supremum on the left and on the right, and those could be different. Now, either on the left or the right, the new supremum is going to be equal to the old one on at least one of the two, but on the other one it could be smaller, which is what happened here. The supremum on the right is the same as the old supremum, but on the left it's smaller. Okay? So now instead of having this width times this height, I'm going to have this width times this smaller height plus this width times the original. Add those together, it's less than this. So this is the reason why adding new points could only make the upper sum go down. Right? There are details here, so I would like for you to know how to prove this formally. And there are details that have a lot of details that I'm leaving out, so I would like for you to be able to fill in those details. So we've defined upper and lower Riemann sums. We can define upper and lower Riemann integrals. So I have integral. So a reminder, f is a bounded function on the interval AB. Okay. So I'm drawing the integral symbol AB, f of x dx, and then a bar over it. The bar over it indicates that it's an upper Riemann integral. Okay. And it's just the infimum of the upper Riemann sums, and the infimum is taken over all partitions of the interval AB. The lower Riemann integral is, the symbol is with the bar beneath it instead of above it. It's the supremum of the lower sums. Again, the supremum is taken over all partitions. Okay? And we say the function is Riemann integrable if the upper sum equals the lower sum. Okay? So I'm going to note that the upper sum is always greater than or equal to the lower sum. So integrability means they're equal. Right? If I want to show that these two things are equal, all I really need to show is that the upper sum is less than or equal to the lower sum, because I know, well, I didn't prove it, but it's pretty obvious. I know that the upper sum is greater than or equal to, so if I want to prove that they're equal, all I really need to do is prove that the upper sum is less than or equal to the lower sum. Okay? So we say a function f is Riemann integrable on AB if the upper Riemann integral is equal to the lower Riemann integral of that function on that interval. Okay? In that case, we define the value of the integral to be the value of the upper Riemann integral, which is, in that case, the same as, right? So if it's Riemann integrable, then these two values are equal. That's the definition of Riemann integrability. And if they're equal, then the integral is just the common value of those things. Okay. We can also define upper and lower Riemann-Stieltjes integrals, and it's exactly the same thing. I take the infimum over the upper sums over all partitions and the supremum of the lower sums, but the lower sums are now the ones that involve these f functions, which are weighting the intervals differently. If the upper and lower Riemann-Stieltjes integrals are equal, then we say the function is Riemann-Stieltjes integrable with respect to this function capital F, and we define the integral to be the common value. So we have a theorem. If f is continuous on AB, then f is Riemann integrable. Okay. So all of our continuous functions are going to be integrable. Okay. We also have a lemma. So our lemma, I think I'm going to have two lemmas here. First lemma is for any positive epsilon, there exists a positive delta such that if P is a partition whose mesh is less than delta, then the upper Riemann sum for this partition is very close to the upper integral. Okay. Same thing for lower sum and lower integral. Okay. And our next lemma is going to be if f is a continuous function on this interval AB, then for any positive epsilon there exists a positive delta such that for any partition P with mesh less than delta, the upper sum and lower sum for that partition are going to be close to each other. Okay. So I'm going to come back to those lemmas later, but it's pretty easy to see how to combine these two lemmas. So what I'm going to do is say upper integral f of x dx minus lower integral f of x dx by the triangle inequality. Okay, so now I'm assuming those two lemmas are true, and I'm going to prove the theorem using the lemmas, and then we'll come back and prove the lemmas. So f is continuous on AB, then it's Riemann integrable. I want to show that the upper and lower integrals are equal. So I'm going to have less than or equal to AB f of x dx upper integral minus upper sum for some partition that we're going to choose later, plus lower sum for some partition that we're going to choose later, plus lower sum so now if my lemmas are true, so for any epsilon there exists a positive delta such that if P is a partition whose mesh is small, then the upper sum for any partition whose mesh is small, the upper Riemann integrable is as close to the upper sum as I want, and the lower integral is as close to the lower sum as I want, and the upper and lower sum for the same partition are as close as I want. So now, if I fix in a positive epsilon, I can find a positive number delta 1 satisfying the conclusions of this lemma, and a positive number delta 2 satisfying the conclusions of this lemma, and then I'll let delta be the minimum of delta 1 and delta 2, and then I'll pick any partition whose mesh is less than that, and then I get less than 3 epsilon. Less than epsilon for that one, because of this condition. Less than epsilon for that one, because of this condition. And then less than epsilon for the third one, because of this condition. And so this difference has absolute value less than 3 epsilon. And because I can do that for any epsilon, that means that this number, this absolute value is actually equal to 0. Right? So this absolute value is less than any positive number. So it's equal to 0, and that means the upper and lower integrals are equal. Okay? So all we have to do now is come back and prove these two lemmas. And we'll do that in the next lecture.